Yeah, this tough audience. Happy birthday.
Thank you.
I apologize for the delay, but I think I'm really not responsible for that one. Better later than never. So you're 60 now, right?
Yeah, counting backwards.
65 minus 5.
Not BPS.
Well, I had lots of photos to show, and I decided to show only a handful of them. Some of the people are here in the audience, and others are here in spirit. Guess they couldn't come. They are kind of characteristic of our interactions. Always good food on the table. Always a lot of fun. And looking at Jeff's eyes here, look at the two photos, you can see that he prepares a fantastic penetrating joke, probably about me. Talking about jokes, Jeff is a great after-dinner speaker. He gave, in my birthday, he gave the second funniest after-dinner speech he ever gave, which was very funny. Not as good as the first one. I'm really looking forward to see how well Paul will do tomorrow on the jet ski. So here are photos from that fantastic after-dinner speech. I'm not going to tell any jokes because I will not be able to follow that act. Instead, I thought I would quote something from his speech, but apply a Z2 transformation to it. This is copied literally from his, not as scary as it could have been. And you can read it yourself. But this paragraph does not really do justice to our interaction over the years. We have had many, many conversations, and they were absolutely fantastic. My research was influenced by Jeff to a huge amount, so thank you for that. Jeff has an incredible ability to take a complicated abstract topic, for example, moonshine or other things, and express it in simple, down-to-earth terms. And this simplified understanding often leads to far-reaching consequences. This strategy has served him well, leading to many groundbreaking papers. I'm not going to discuss any of that here. Jeff and I also spent a lot of time talking about politics, and even more so academic politics. And I'm not going to discuss. I promised. I took my promise. I'm not going to say anything about that, except to say that one, our views are identical to each other, completely identical on every topic, which guarantees that I'm not going to say a word about it. And second, he was also very helpful in academic politics when he served on our board. And in that context, he rescued me more than once when I was just about to say a very incriminating comment, and he diverted the conversation as he anticipated that would happen. He knows what I'm talking about. I'm not going to say anything more about it.
But where are the Trumpian quotes?
Whose quotes?
The Trumpian quotes.
Whose quotes? So this brings me to this talk, and I thank the organizers for inviting me. And it's traditional in this is kind of high energy condensed matter interplay, the topic. And it's traditional in condensed matter physics to show photos of the collaborators. So I decided to give a typical photo of our collaboration. That's it. So you can see my three collaborators. And not only did they do a lot of the work, they also helped preserve my mental health during the pandemic. We had these daily conversations. So this finally brings me to the talk. And this is a subject that really stressed my understanding of quantum field theory over the last 2 or 3 years. I thought I knew quantum field theory, but I realized that I really don't. And the point is that there are these exotic models, Lifshitz model, I'll talk about that. There's something called the XY plaquette model. There are various fracton models and many others, and they do not have a standard continuum limit. So they're defined on the lattice in the simplest form using ordinary degrees of freedom, circle valued, or spin up and down, or ZN spins, etc., with some local interactions. Looks very conventional, is innocent-looking Hamiltonian or Lagrangian. But the long-distance behavior or low-energy behavior is not captured by a standard quantum field theory. And this is a huge challenge for anybody my age who was brainwashed. I think also somebody's Jeff's age, who was also brainwashed that this shouldn't happen. If you start with something local at short distances, no matter what you do, at long distances, it would be a field theory. Maybe a gap theory, maybe a conformal field theory, maybe topological, maybe not, but it should be a standard quantum field theory. This prejudice is wrong. There's no question about that. And this is a huge challenge to our understanding of field theory. In this challenge, or this, to write a quantum field theory description of these systems, originates from the peculiarities of these models. So most of these models are solvable. These are solvable lattice models. You know the answer, and the question is, what do you do with the answer? How do you summarize the low energy behavior using field theory? So this is a lightning review of the subject. There are either emergent or exact, very unusual global symmetries that depend on position. Not ordinary global symmetry that you rotate phi everywhere, but you rotate phi in a position-dependent way. That's not something common. Second, there are excitations with restricted mobility, particles that are restricted to be at a point or restricted to move on a line, etc. What do you want to do? Maybe better not to.
Not to?
No, it's okay. You can record. And they also have a crazy ground state degeneracy. So the ground state degeneracy is a formula that depends on the number of lattice sites, typically of the form 2 to some function of the number of sites in the x, y, and z directions. But the limit Li goes to infinity is not a well-defined limit. So depending on how you take L to infinity, this k could be a finite number, as it is in standard theories, or it could diverge, and it could diverge at different rates. This is not, so if we want to say that L goes to infinity is a quantum field theory, we'll have to explain what this formula means. They also exhibit what we can call UVIR mixing, where long distance properties are very sensitive to short distance properties. If you try to remove a UV cutoff or an IR cutoff, these two operations don't commute. This is again something that does not happen in normal field theories. And there are many other peculiar features, and some of these models exhibit some of these peculiar features, other models exhibit other peculiar features. So this is something that we should understand and explain. So we can try and follow our nose, look at the lattice model, try and take the continuum limit in an obvious way and find the Lagrangian, and then explore the Lagrangian. I want to emphasize that most of the lattice models that I will discuss here, and most of the continuum models that I will write down, are not original. They had been studied long before we moved in. So you cannot say, oh, these are crazy continuum Lagrangians, why are you interested in them? Well, we didn't invent them. This is something that exists in the literature, so this is something that we ought to understand. So if we do that, we find some examples of continuum Lagrangians that we would like to understand. And schematically, they look like this. So the Lifshitz model that I'll talk about today is a standard time derivative term. And then the spatial derivative, we don't have two derivatives, but we have four derivatives. And we can sum over all I and j are the spatial direction. We can sum over all I and j. We can sum only over I and j with restricted trace. We can sum over all I and j, but I not equal to j. There are various different models we could study. And every one of them has its own peculiar features. We can also study similar gauge theories. These were originally introduced by Xu, he's a condensed matter physicist, and by Xu and Wu, also a condensed matter physicist. They wanted to have emergent gravity arising out of the lattice. Personally, I think this is totally misguided. You shouldn't look for gravity emerging out of a lattice system, but that's what they wanted to do. And For that reason, they introduced, instead of a vector potential, a tensor potential. So A has two indices with this gauge principle. So instead of having first derivative here, we have second derivatives here. So that's what they did. And the interesting thing about this model is probably not good for explaining gravity. However, Pretko noticed, and I will review it soon, that if you take that as given, then this behavior, such a gauge theory, leads to particles with restricted mobility. And I'll explain that in more detail. Again, the characteristic property is that we have terms with double derivatives, like here and here, and also here. And these double derivatives lead to all sorts of singularities that we will have to discuss. And once we have gauge theories, we can have various BF theories. Again, this is kind of a standard thing that we often do. And there are many, many other examples with all sorts of Lagrangians. So as I said, the higher derivatives lead to important subtleties that we're going to discuss. So you could start the talk by saying, I'm not interested in the lattice, I'm a high energy physicist, I'm doing continuum quantum field theory. I don't want to hear about the lattice. I just want to study theories that this is the Lagrangian. This is a valid question. Or you could ask, I'm a condensed matter physicist, the lattice is real. Don't confuse me with the continuum Lagrangian. I just live on the lattice and I'm perfectly happy with that. And all these views are perfectly acceptable. So let me summarize the kind of questions we would like to ask. First of all, what do such continuum field theories mean? We learned continuum quantum field theory from your favorite book. So we can just follow our nose and analyze the theory, right? More decompositions and so forth and see what we find. One thing that immediately comes, right, is that because of these higher derivative terms, it's unavoidable to use discontinuous fields. Discontinuous fields are not suppressed by the action. Usually we don't study discontinuous fields because discontinuous fields are suppressed by the action. That might not be the case here, depending on the model. The second question, which is extremely interesting and important, is what are the global structures? We had a scale of, yes, Andy.
I have two questions. One is, if you've got more derivative, doesn't that make discontinuous fields worse?
So imagine you have only dx dy phi quantity square, no dx square phi, but only dx dy phi quantity square. So a function which is discontinuous in x independent of y is not suppressed. And so there are many different models, and like every one of them has different peculiarities. I will soon give one of them, I'll soon analyze one of them in more detail. And then the subtlety will not be discontinuous functions, but functions with arbitrarily big derivative.
Is it possible, a completely different question, is it possible to summarize, so we're interested in relativistic theories because a continuum limit is a good approximation for many things that we, and continuum limit is also important in many contexts in condensed matter physics. Is it possible to summarize how this fits into the experimental?
Okay, so these models are not relativistic.
Right.
All these models are not relativistic. Many of them do not even have spatial rotation symmetry. They hold like only a discrete subgroup of it. The experimental situation, the simplest models do have realizations, but the more interesting ones do not have an experimental realization now. But there's no reason in my mind why there shouldn't be one. In fact, people already discuss some possible technological implications once these materials are described, are found. So there's a lattice system that we know how to analyze. There's huge theoretical work on it. It could be, people look for these materials exhibiting this, but then if you do that, there would be fantastic quantum memories. For example, I mentioned the large ground state degeneracy. That's what you need for a quantum memory. So there's a huge incentive to find these materials that exhibit this. But I'm kind of taking a more, a simpler view. There's a field theory, it's not a field theory. What is it? Should we extend what we usually mean by field theory and study these? Should we not? Maybe we should abandon field theory altogether. There is a real confusion here, or puzzle. So we would like to understand the global structure. So I had gauge theories. Are fluxes quantized? How are they quantized? Are charges quantized or not? Are there magnetic charges or not? All these questions need to be addressed, and we'll see that in examples soon. Second, what's the relation between these continuum theories and the underlying lattice model? We started with some lattice model, and we said we take the naive continuum limit, that's what we find. What do they have to do with each other? Do they lead to the same answer or not? As you will see, the lattice model is completely well defined. You can put it in computers. Many of them are just analytically solvable. You can just analytically solve the lattice model. And as you take the limit, it is singular. What does this singularity have to do with the continuum Lagrangian I wrote? And I'll give more examples. More generally, how should we organize such theories? We would like to organize them because this would give us some kind of a classification, but it will also give us a way to think about them. Personally, I think that we have seen only the tip of the iceberg of these crazy models. It's quite likely that there are many other possibilities that we have never seen. And people stumbled on these examples. If I have time at the end and you're interested, I can tell you about the history of this. It's fascinating how these examples were found. They were not found by any systematic search. And there might also be more examples. So what I'll do here, I'll take a high energy physicist perspective. I'll take the absolute simplest example of these systems that is not as rich as the more complicated one. The more interesting models are in 3+1 dimensions. I'll talk about the one in the smallest number of dimensions, which is 1+1 dimensions. So this will be a system in 1+1 dimensions. It is not as rich and not as interesting as its higher dimensional counterparts, but a field theory is a walk, so this says, what is this thing in this lowest number of dimensions that we can study? And it has few, even if it doesn't have all the features, this is a good starting point. So finally, after this long introduction, I can start the talk. And this is the Lifshitz Lagrangian, which was analyzed by a lot of people over the years. There's a standard kinetic term in time, and in space we have a 4-derivative term. And most of the literature is phi being a non-compact field, but we are going to take phi to be identified with phi plus 2 pi. So this is the problem. This is something, if you teach quantum field theory, you can basically give it to your students. It appears not that much more difficult than a free compact boson in 1+1 dimensions. Don't give it to your students because it's really quite subtle. First question is it natural? After all, I dropped the 2-derivative term. Why did I drop it? Well, natural means that there's a symmetry that kills it. So we kill it with the symmetry. So this model has a symmetry which can shift phi by a constant. And since phi is circle valued, C is circle valued. Also, we can shift phi by a term linear in X. If we shift phi by a term linear in X, these two terms are invariant. But if we put a 2-derivative term, dx phi quantity square, it will not be invariant under this shift. Such a shift symmetry is called the dipole symmetry, and it's very common in the literature in condensed matter physics. So we have a symmetry. The textbook tells us what to do. C is identified with C plus 2 pi, so the symmetry is U1. So the symmetry associated with this C is U1, and the Netter procedure. This is the Netter current. This is J. This is the time component. This is the spatial component. This is what the conservation equation looks like. And the conservation equation follows from the phi equation of motion. So that's something that your graduate student who studies quantum field theory can derive. And the conserved charge is the integral over space of the time component. So that part is relatively easy. But the dipole symmetry, superficially, is also easy because we consider this combination x times jt, and it's also conserved because I hit it by d by dt, and I use the conservation equation. We have 2 derivatives. I integrate by parts, so I can kill this x, and that's what seems to lead to the shift linear in x. However, this reasoning is wrong. This reasoning is wrong because we have to be very careful about the boundary conditions. And if we make a shift of phi by something which is linear in x, it changes the boundary conditions at infinity, so we have to be a little bit more careful. So let's be more careful. First of all, so we are going to put space on a circle so that we don't have to be confused by what's going on at infinity. We put it on a circle with periodic boundary conditions. So x is identified with x plus L. And now, if phi is non-compact, this shift is not compatible with the boundary conditions anyway, so we can just cross out this term. If phi is compact, we can perform such a shift provided the coefficient is quantized in units of 1 over the length. if the coefficient is quantized in these units, such a shift keeps a boundary condition of phi consistent because it shifts phi by phi goes to phi plus 2 pi. So what we see is that as a group, the ordinary momentum symmetry, the C is U1, but the dipole momentum symmetry is actually Z. It's a discrete group. It will soon have consequences. Now, we can also consider such winding configurations. This is what we do in the compact boson. When we perform this dipole shift, it changes the value of M. This means that this winding configuration has zero energy. You can just put it in the action and check that this winding configuration has zero action and zero energy. This already, so you start seeing that the model starts being crazy. The winding configurations cost you zero action, is zero energy, and as a result, every state in the spectrum is infinitely degenerate. Take any configuration you had, put any winding mode on it, and it still has zero action and zero energy. In fact, we see here a baby version of the UVIR mixing that I talked about before. We have zero energy states, that's in red for IR, and we can have it with arbitrarily large spatial derivative. So this is also in response to Andy's question. Here, the field configuration, the configurations have to be continuous, but the slope can be arbitrarily large and we still have zero energy. This is not something you have seen in an ordinary field theory problem. You see that this system is getting crazier and crazier as time progresses.
Nati, you said that it was natural because this shift symmetry, depending on X, forbids certain interactions. But when you argued that, we were thinking of CX as an arbitrary number, and now we've learned it's quantized.
No, even if it's quantized, as a symmetry, imagine you add d phi dx phi quantity square. Even when it's quantized.
Well, you can't add dx phi quantity square, but is there nothing else you can add?
What else? You can only terms with more derivatives. There are terms with more derivatives you can get.
Yeah.
So I'm writing
cosine or something involving derivatives or something. I mean, there's nothing you can add.
No, there's nothing you can add. There's nothing you can add that respects the symmetry. That's correct. Yes, Andy.
Do we have reason to think that quantum effects or the continuum limit would these things?
That's the heart of the matter. This is exactly where I'm heading. So it seems that I'm doing a good job because Andy always asks me about the next step in the talk, as if he looked at my slides. Okay, as high energy physicists, we say, oh, then maybe there's a winding symmetry. After all, I already discussed winding modes. And you know, this is a conserved winding charge. It's d by dt of this is d by dx of this. And there's a winding charge, q tilde, the way we normally have. It doesn't depend what the action is, we just count how many times phi winds around. But as I said before, the Z momentum dipole symmetry, the one that shifts phi by a term linear in X with an arbitrary integer, does not commute with this U1. Because as I shift phi by that, I change the eigenvalue of U. In a fancier way, I could say that there's a 't Hooft anomaly between the Z dipole symmetry and the U1 winding symmetry. So between the Z dipole momentum symmetry and that, but you don't need the fancier language. You see from here that the symmetries don't commute. And since the symmetries don't commute, you have an infinite degeneracy. Because the smallest representation of this algebra of Z and U1, where the Z and the U1 don't commute, has an infinite number of states. At this point, you should be very nervous that you see that this is an innocent looking continuum Lagrangian, but I'm walking here on very thin ice with things with infinite derivative, infinite degeneracy. Is this analysis sensible? And the only way to answer that is to regularize the system. So I'm going to discretize the system and see what happens when I regularize it to see whether the discussion here really makes sense. So we're going to put the system on the lattice with L sites in space. So I'm not going to do it in detail because I don't have too much time, but I can put it on a Euclidean lattice. And this is the action. Don't pay attention to the details. The details are not important. This is a lattice action. And he has some fields. Some of them are integers. Some of them are circle valued. this lattice action is very good because it has all the symmetries that I had in the continuum. So let me say that in a little bit more detail because it is interesting. As far as the momentum symmetry, there is a U1 that shifts phi by a constant. That's obvious. And there's a ZL momentum symmetry. We shift phi by a term linear in X, and we are on the lattice with L sides. There's also a winding symmetry. There's a U1 winding symmetry that shifts this phi tilde by a constant, and a ZL winding symmetry. And these two ZLs do not commute. This is just property of this lattice action. L is the number of sites in the lattice. So the global symmetry group of the system depends on how many sites the lattice has. And now we can take the continuum limit. We can take several different continuum limits. Depending on how we take the continuum limit, we get different answers. So what we need to do is take L to infinity, the number of sites to infinity. And this first thing to discuss is what happens to the group. I know that Jeff loves groups. So the first thing, take L to infinity, what happens to the group? And what is the limit of ZL as L goes to infinity? This question has several different answers. The limit of ZL as L goes to infinity could be Z, or it could be U1, depending on how we take the limit of which representations we take. This is a correct group theory statement. And what happens here is the different symmetries of this lattice become different in the continuum limit. So this U1 remains U1. This ZL becomes Z. This U1 is gone, it doesn't act on light states, and this ZL becomes U. So these two ZLs, which don't commute on the lattice, become this Z and this U1, which do not commute in the continuum. So by doing it this way, I presented a completely regularized version of the system. In this lattice model, nothing is infinite, everything is regularized, everything is finite, everything is calculable. And if we take L to infinity, in a particular way, you recover the answers we got in the continuum. There are, however, other ways of taking the limit, scaling the parameters differently, and they lead to different theories. I'm not going to discuss it here. So what field theories usually do, we discuss a model and it has a global symmetry. The next question to ask is, what is the corresponding gauge theory? We have a global symmetry, how do we gauge it?
So could you say more about what the symmetry actually is? Because you said there's U1 times Z for momentum, and there's a U1 from winding, but the U1 from winding doesn't commute with the Z from momentum.
Right, so
what is the actual
okay, so there's a question of what you mean by symmetry group. My definition, which is actually Wigner's, that the symmetry group is how the symmetry transformations act on operators, not on states. And so the symmetry group is a central extension of U1 times Z. You're more familiar with the central extension of ZL times ZL. There's a standard central extension, which are the clock and shift algebra. So the group is ZL times ZL. It acts on operators by commutations. Therefore, you don't see the central extension in the action on commutators, but you do see the central extension when you act on states. That's why the Hilbert space can be in a projective representation of the symmetry group. And at this point, I'd like to thank Clay for teaching me these things. Well, Wigner also taught me these things.
We were contemporaries.
What's that?
I said we were contemporaries.
Yeah. You did age a lot. So what do we do? So again, we follow the textbook. We have a global symmetry of a matter system, and it has a conserved current with this conservation equation. So we write JT times AT and J times A, and we learn what the gauge transformations should be by looking at the conservation equation of the current. So this motivates us to study this gauge theory, and now we can throw away the matter theory and just study the gauge theory on its own. What's the gauge theory? How should we think of it? So these are the gauge transformations. It's called the tensor gauge theory because in higher dimensions, this AXX is AIJ. I suppressed these indices because we are in 1+1 dimension. I wanted to make life as simple as possible. And there's a Lagrangian. So again, we are in this situation that there's an innocent looking Lagrangian. The only thing which is subtle is these two derivatives here, with this gauge symmetry with the two derivative here. And our goal is to analyze this Lagrangian. So we ask ourselves, what does this gauge theory mean? So this is again something that in principle you should give your quantum field theory student. Here is a Lagrangian what do we know about it? In particular, what are the global properties of such a gauge theory? Do we have the notion of parallel transport or not? How should we quantize the Wilson lines? What are the magnetic fluxes, etc., etc.? So in order to answer this question, we put the system on compact space-time. Here, I'm going to Euclidean space. Tau is Euclidean time, T is Lorentzian time. I compactify tau on L tau and X on L. And since phi started its life as this compact Lifshitz theory, it was circle valued. So I'm going to postulate that this alpha is also circle valued. So this is my starting point. And now I'm just following my nose. I should study large gauge transformation. So there's a large gauge transformation on the torus, which winds n tau in the time direction, and nx in the space directions. And the large gauge transformation should tell us how the various Wilson lines are quantized. That's what we normally do. So for defects, and this is something that Greg, I don't know if he listens, always tells me, you should distinguish defects and operators. Operators act at fixed time, defects stretch in the time direction. And in a relativistic system, that's not a big deal because you can always rotate one to the other. Our system is non-relativistic, so I'm going to pay a lot of attention to Greg's instruction. I'm going to distinguish defects and operators. Defects will be used, I'll always use this color, this red color, and for operators, I'll use this blue color. I hope it's visible. So for the defect, the running in the time direction, the transformation in time is standard, so the coefficient here must be quantized. That's not the case for the operators. This operator is gauge invariant because the second, so one derivative kills x, and then you might need to worry about the periodicity, but the second derivative kills it anyway. So in this, when we integrate around x at fixed time, this operator does not need exponentiation, and there's nothing quantized about it. So the defect is quantized, and it represents the word line of a charged particle. So it's a charged particle at the position x, then in time. Notice that we don't have a spatial component of the gauge field with an index x that would allow this guy to move in the x direction. It is stuck at one point in space, and because of the gauge symmetry, it cannot go anywhere. It's not a question of energetics. You can pump as much energy as you want, it cannot move. And so this operator is quantized, this defect is quantized, but the operator is not. In fact, this object has dimension 1, so it doesn't even make sense to exponentiate it. So at this point, I would like to have a little digression and tell you things that you already know, but in a new language. So what I'm going to do now will be kind of really splitting hair about something that you know, but it will be very important in what I'm going to say later. So I'm going to start a standard U1 gauge theory in any number of dimensions, Maxwell theory in any number of dimensions. So a standard U1 gauge theory has a one-form electric global symmetry. And the global symmetry shifts A mu by a constant, lambda mu divided by L mu. And this lambda mu is circle valued. This is the statement that an ordinary U1 gauge theory has such a global symmetry. It acts as a global symmetry on the system. It gives the Lagrangian invariant, and it's not a gauge transformation. So it is a genuine global symmetry. And recently, such global symmetries have attracted a lot of attention. We are interested in a non-relativistic system. In a non-relativistic system, we should study A0 or AT and AI separately. So let's see what they do. For the spatial component, this is completely straightforward. We just shift AI by a constant. It acts as a global symmetry. It acts on the states in the Hilbert space, and it acts on the operators. So this is an ordinary symmetry, and that's why I continue my color coding, and it's the operators are like that. In the time direction, lambda tau does not act on the Hilbert space, nor does it act on any operator at fixed time. So the Hilbert space of Maxwell theory, the time component of the one-form global symmetry doesn't act on anything. Instead, it acts on the defects. The defects of the system, these are not operators in the system, these are defects that stretch along time at fixed x. The defects depend on them. So if we talked about this defect, you see that if I shift by lambda tau, it picks this phase. So this is a way of saying that when we say that the defect carries charge M, what we really mean is that under a time-like, we'll refer to such symmetry as a time-like symmetry. So it means that under such a transformation, the defect carries charge M. Notice that the standard way of thinking about, oh, this is a particle of charge M, it's a little bit imprecise because there are no particles in the system, and the charge under U1 is a gauge charge. So what does the gauge charge mean? So this is the precise way of saying it. Now, at this point in time, you might think, why is it telling us all these things? It's well known, we already know that. Well, I'm telling you that because when we come to the subtle systems, this language turns out to be enormously effective. That's the way we need to think about the defects and the operators in the tensor gauge theory. So we're going to do the same thing in the tensor gauge theory. So we have two kinds of gauge fields, space component and the time component. So the space component is a space-like global symmetry shifting A by a constant. This was A, which was really AXX. So this group is R. It acts on the states and on the operators. In the time direction, there are two kinds of transformation we can do. We can shift by a constant, or we can shift by a term linear in X. Again, don't try to reproduce the details. These are the transformations that leave the action invariant, and they act on the defects. And the defect, e to the I m, that picks a charge m, as I said, it picks a charge m, and the dipole charge is phase. So again, recall that the dipole symmetry is, so the time-like symmetry is for the charge, it's U1, and for the dipole charge, it's Z. So the group is Z, the transformation is labeled by an integer, in this case, n, and the charge is circle valued because the group is Z. If the group is Z, the charge is a point on a circle. So that's the global symmetry, and I comment that not coincidentally, it's like the global symmetry of the momentum global symmetry of the Lifshitz theory. So we started with the Lifshitz theory that has that as a global symmetry. We gauged it, and then we threw away the matter. The time-like global symmetry, the symmetry that acts on the defects of the gauge theory is the same as the global symmetry of the Lifshitz theory we started from. And this is not a coincidence. Now let's diagonalize the Hamiltonian. How do we diagonalize the Hamiltonian? This is the standard thing we do. We pick temporal gauge, and then we impose Gauss law. So Gauss law tells us that second derivative of E vanishes, and we substitute it in, and we find a spectrum which is continuous. So the states in the spectrum are labeled by a real number Q. There is a continuum of states, even in finite volume. And the states carry charge under this R global symmetry. What about the defects? These are the defects, and they carry these charges under the time-like symmetry. And these charges tell us that this defect cannot move. Before I said that the defect cannot move because we don't have the spatial gauge field to allow us to bend. Now I say that it carries charge. I don't even need to understand how we constructed it. There's a global symmetry. And since we have a global symmetry, this object carries charge 1 under the U1, and charge e to the 2 pi I x over x L under this Z. That's a global symmetry of the defect. And if we shift it to another x, this charge will be different, and therefore the object cannot move. So I phrased the restricted mobility in terms of a global symmetry of the system. We have a system with defects. These are not symmetries of the Hilbert space or of the operators. These are symmetries of the defect. And the symmetry of the defect is such that it prevents the defect from moving, because a defect at one point and a defect at a different point, they carry different charges. This allows us to state something that Pretko had already said, and I didn't understand it when he said that. The charge particle carry an ordinary charge and a dipole charge, and therefore they are immobile. So Pretko said that. This was the motivation to study these theories. I couldn't understand here whether we are in finite volume or in infinite volume, and what we mean by charge when this is a gauge charge, and in finite volume, the total charge is 0 anyway. So what are we really talking about? And I tried to give here a more precise statement that corresponds to that.
Can you violate the symmetry that makes them immobile by an operator deformation in the theory?
No.
Can you violate it by coupling to something like charged matter?
No. I can check if I have massive charge matter, it doesn't move. I have to do something a lot more sophisticated to do that.
What do you have to do?
I have to add a lot more particles to do that. I have to do something much more sophisticated because this is really it's the same as asking, can you violate the one-form global symmetry of massless particles? So there in QED, you can add that by adding massive particles.
Yes.
Here you cannot. Because the massive particles will also need to be subject to this shift symmetry with X. Because you have to do it in a gauge invariant way, so you can't do that. But I'm a low energy person, and the low energy person studies the low energy field theory. The low energy field theory, this gauge theory with the defects, so this spirit here is that I don't know what you do at short distances. I don't care about that. I'm only trying to analyze the low energy effective theory. The next slide, I'll put it on the lattice, and then you can ask your question again. So here we phrase it in a gauge invariant way, finite volume, and it makes sense. I really like the fact that the restricted mobility follows from a symmetry. This is something that I really wanted before. If particles of restricted mobility, this should reflect something. And the something that I always go after the symmetry. This has been a theme in my work. Always try to understand the global symmetry. Global symmetries are meaningful. They do not depend on which gauge, whether we describe it as this gauge theory or that theory. This is an objective property of the theory. And now we formulate the restricted mobility as a consequence of that global symmetry. Again, you could ask, does this discussion make any sense in the continuum? Because you might be nervous that maybe it doesn't make any sense, What about all these symmetries? Do we really have them or not? So we go to the lattice. I'll be very brief. We studied the system with the Euclidean lattice with periodic boundary conditions. And we put the gauge fields on the time-like links. This is completely standard. This is what we normally do in gauge theories. But because of the funny gauge transformation laws, we put the spatial components on the sides. So in the time direction, the gauge transformation acts at the two ends of the time-like link. And in the spatial direction, it's kind of a Laplacian that acts among two sides. And this is the action. It's kind of quote unquote the Wilson action for this theory. We look at all the time-like links, and we write such a cosine of these phases. These are lattice derivatives. It's gauge invariant under this gauge transformation on the lattice. And again, I'm going fast. It might not be easy to follow, but this is a well-defined lattice model. A and A tau are phases. So if we have a finite lattice, there's a finite number of integration variables, A and A tau. Every one of them is a circle, so the integral converges, and we can just do the integral, at least in principle. There are other versions of this action that you can actually do the integral. And this lattice model has global symmetries. So now everything is completely kosher, everything is regularized, and I just ask myself, what are the global symmetries of this action? In other words, how can I shift the gauge fields on the lattice such that the action is preserved? Paul.
I'm just curious, you had said at the outset that many of these lattice models were already defined. Is this one of them, or is this one?
This particular one was actually written before. This particular one was written before, not quite in this way, but morally it's the same.
By whom?
Hermele and others. I forget the co-authors. I think Chan, Hermele. I might have the reference.
When was it?
It's all in the last 3, 4, 5 years. No, I'm not talking about, it's not our generation. These are younger people. There are such people, not your generation. I think I should not say. Okay, so what is the symmetry? So we have a well-defined lattice action. We just forget where it came from. We just analyze the global symmetry. So we have a time-like symmetry. So we have a space-like symmetry shifting A by a constant. This is a symmetry on the lattice. And we have a time-like symmetry shifting the time component by this. So we can shift by a constant and a term linear in X at 1 tau. You can check explicitly using the lattice action that I wrote that these are two symmetries. And now we see that we have a U1 space-like symmetry and U1 times ZL time-like symmetry on the lattice. And this U1 can be interpreted as the charge. This U1 factor can be interpreted as the charge, and the ZL is the dipole charge. And once we have a lattice action, we can take the continuum limit. And we can take ZL to infinity, we take L to infinity. And the first thing to ask before we get into all the details of what we do with the coupling constant and so forth is what happens to the group. Because the theme is always there's a global symmetry, check what happens to the symmetry. So I ask, what's the limit as L goes to infinity of ZL? Depending on how you take the limit, the group ZL in the limit L goes to infinity is either the group C or the group U1. There are two ways of taking the limit. And so we could do that. One of them gives us the answer that we wrote before, and the other gives us something else. So in the continuum limit, this U1 becomes R, this U1 remains U1, and this ZL becomes Z. And this is precisely the space-like and the time-like symmetry that I had before when I discussed the continuum. And as I said, as in the matter theory, we can take different limits, and if we take different limits, we find different continuum theories. And you cannot ask which limit is the right one. You know, I talk to people, I don't want to give names, so they would ask, which one limit is the right one? Well, all limits are right, they just explore different range of parameters. And I think we should explore all of them and see what we learn from them. How much time do I still have? With the chair?
No, 10 minutes.
5 or 10 minutes, oh, plenty of time. So I'm going to briefly go through a ZN gauge theory. And I could do that in the continuum, but I prefer to do it on the lattice because this will be a lot faster now. And it will be manifestly correct because on the lattice, everything is manifestly correct. There is no room for what exactly did you mean by this or that? Because everything is just ordinary calculus. So we do it on the lattice. And we take what we did for U1, and we put phases on the sides and the links. And now whenever there was a phase, we just put a ZN phase. That's the rule. This is how you construct ZN gauge theories. So in the U1, we put phases A tau on the time-like links and e to the IA on the sides. And I will do the same thing, except that these will be integers modulo n. So we take the same thing we wrote before, and we take integers modulo n. So in ZN gauge theories, there are always configurations with non-trivial plaquette. In ordinary ZN gauge theories, there are configurations with non-zero plaquette, there's local curvature. And the continuum gauge theory corresponds to configurations where every plaquette is trivial. So the previous speaker talked about orbifolds. He says you couple to a ZN gauge theory. What that speaker meant is you couple to a continuum ZN gauge theory, and in the continuum ZN gauge theory, we restrict all the plaquettes to be trivial. So we'll do the same thing. You compute the gauge invariant thing, and we'll just force it to be zero. And you can force it using the Lagrange multiplier. So this is our final action. It's a lot simpler than what I had before because I restricted to low energy fields. I put a Lagrange multiplier M tilde that forces this guy to vanish. And this way, our action is actually quadratic. We could have done the same trick in the U1 gauge theory and in others. So we have an action which is quadratic in the fields. It's kind of a free action, but it has a lot of gauge symmetry that you should analyze carefully. So this is our lattice action. M and M tilde are integers modulo M. So the partition function is a finite sum. It's a finite sum over a finite number of, every variable goes over n values. And you have a finite number of variables. It's completely well defined. So this is the action. And now we would like to analyze this system. Question, what's the ground state? Well, the ground states are the solutions of these two lattice equations. We have to solve the delta Laplacian of M, lattice Laplacian of M tilde is 0 and the time Laplacian is 0. Forget where it comes from, you can sort of believe that this is where it comes from. So these are the equations we have to solve, and we ask ourselves how many solutions are there? This is a well-defined problem on the lattice. How many solutions does this have? And the number of solutions is n times the greatest common divisor of n and L. The number of solutions depends on the number of sites in the lattice. This is actually a rather familiar thing in lattice systems, that the number of ground states depends on how many sites we have. In this case, so similar formulas exist. in the higher dimensional version of this problem, the number is exponential of such factors. So it's a lot larger than what we normally see, but that's what we see here. It's always between n and n squared. But another interesting feature of it is that depending on how we take L to infinity, we get a different answer. Always a finite answer, but a different answer depending on how we take L to infinity. So the continuum limit is kind of ambiguous. But this is the number of ground states, at least on the lattice. Now let me say something about the defects. So the basic defect is such a Wilson line in the time direction. It's gauge invariant. But unlike the U1 gauge theory, here the defect can hop. We can put this object, we can put this object in a fixed point at x equals 0 at negative time, at x equals n at positive time, and in between there's an operator, and hence the color is blue, that hops the particle. So the particle can move from one point to another. So we see that in this case, unlike the U1 problem, in this case, the particles have restricted mobility, but the particle can hop by n units. And using the lattice periodicity, it can actually hop by the GCD of n and L. So the restricted mobility of the particle depends on how many sites we have on the lattice. And related discussion is that this is the paper that this other action appears. Ma, Hermeli, and Chen. I remember two authors, and that's what they did. So let me summarize. This is a huge field. I didn't do justice to the field. I picked the absolute most trivial example in 1+1 dimensions. It exhibits many of the subtleties, but not all of them. Exhibits some of the peculiarities, but not all of them. As we go up higher in dimensions, especially to 3+1, it's a lot crazier. And as it's a lot crazier, it's much more interesting. But this is a good pedagogical example to keep in mind. And some of the techniques from here can just be copied there. Again, you can write quadratic actions, you go after the global symmetries, you make sure that the global symmetries exist on the lattice. There are the space-like and time-like symmetries for the gauge theories, and so forth. And we discussed three classes of models. A model with U1, this is the Lifshitz theory, the corresponding U1 gauge theory, the tensor model, and the ZN version of this gauge theory. These three theories in higher dimensions had appeared before our work, so we're not even original about that, except that we gave this more systematic way of thinking about it and how to organize everything in terms of the symmetries, and doing it both on the lattice and the continuum, and being careful about how we take the continuum limit. So we analyzed them on the lattice and the continuum, and we found a number of unusual features which are not standard in ordinary field theories. First, there were strange degeneracies. In the first example, which was the Lifshitz model, there was an infinite ground state degeneracy, or an infinite number of states at every level. And this was finite on the lattice. The degeneracy was L, but in the continuum limit, it was infinite. And this was either infinite or ambiguous, depending on which model. There were defects with restricted mobility. And the mobility could even depend on how many sites we have on the lattice, which is very unusual. These two facts, the strange degeneracy in the restricted mobility, follow from symmetry. And this is something I like very much. Whenever we can explain a property of the model using its global symmetries, we feel we understand something, we understand what causes that peculiar feature. So the ground state degeneracy follows from the space-like symmetry, the restricted mobility follows from the time-like symmetry. And we also saw UVIR mixing, how long-distance phenomena can be sensitive to short-distance details. And we saw how we can have long-distance states, like counting the states in the spectrum, are sensitive to fields with arbitrarily high derivative. As we go higher up in dimensions, we also have fields which are discontinuous in the variables, and one has to keep track of this. So in higher dimensions, there are many more models. There's more room to play with the derivatives. there's a lot more fun that you can do on the lattice. In one dimension, the lattice is just a bunch of points in a circle. In higher dimensions, we can have a cubic lattice or an FCC lattice or triangular lattice. We can have a lot more fun in higher dimensions. And so we've made a lot of progress during the pandemic, but many interesting puzzles remain. And as a last slide, happy birthday, Jeff.
So you showed that there's a symmetry which leads to a conserved charge, which implies the lack of mobility. I mean, I guess there's kind of a stupid argument the other direction. Mobility obviously implies a conserved charge. If it can't move, then its position is conserved. But it doesn't necessarily tell you what symmetry implies that.
Yeah, so let me answer that. In the last example I said, it actually can hop, but in a restricted way. So the symmetry is actually a lot smarter because it tells us by how much it conserved. In fact, if you take a particle of charge 2 in this example, and this is something we found other than fact, we had to put a particle of charge m in general, and they said, okay, let's check the symmetry. And it turns out that the particle with charge m can hop even in more possibilities. And then we realized that this is indeed the case. So this is an example where understanding the symmetry gave us results we didn't have before. So I think if there's one person in the audience here I don't have to convince about the importance of having symmetry and understanding the symmetry correctly. You're not the only one, but I think at least you're certainly one of them. And the power of the symmetry here really helps organizing what we are doing in a more conceptual and more systematic way. So this has been a theme to really understand these symmetries. And this has been a very powerful tool. In these examples, it's relatively simple, but when you do the same thing in the higher dimensional examples, where there are many more moving parts, the symmetry is kind of something that you latch onto. Because whenever you're confused, say, okay, what's the symmetry? And then you get the answer. So putting it the other way, I had not understood before how the restricted mobility follows from a symmetry. I knew that there was restricted mobility, and in some cases there was this dipole symmetry, there was this argument of Pretko, and I honestly didn't fully understand it. Now I understand how to state that in a gauge invariant way. But in other models, which are much more complicated, there's a model called the X-cube model, there's something called Haas code, which is even more sophisticated, there are many others. We couldn't even figure out what the symmetry is. And now that we knew what we were looking for, we went after the symmetry and then we reproduce all the answers using. So that's a much better way of organizing the information.
I had two questions. One, so you mostly showed us free theories. Do you think they're interacting versions of these theories with maybe?
I'm sure they are. So far the free theory was quite subtle. I gave you a glimpse of it. As you go higher in dimensions, it's getting much more interesting. What can happen still when the theory is free. People wrote various, so it's a huge field, and I don't think I can make a blanket statement that covers all cases. And I also think that we know only a tiny fraction of the possible models that could be out there. So I do not know in general, but people did write models which you can call interacting, basically by putting a non-abelian gauge theory in 2+1 dimension, Chern-Simons gauge theory in 2+1 dimensions on a plane, and stacking the planes like this, and then in the other direction and in the third direction, and couple them somehow. So that's, I think, is the state of the art. There are other ways of introducing interactions. Personally, I would go after the global symmetry. Because the global symmetry is an unambiguous way. When you start involving gauge symmetries, under duality, the gauge symmetries change. It's not clear what's important and what's not important. You really have to use the gauge symmetry or not? Should you impose Gauss law on the nose or only using the energetics? Should you add matter fields or not? I get very confused. So I pretend being more confused than I am, but I assure you that this way of thinking about it is a lot clearer.
And another question I had is, so you probably want these symmetries to be emergent for them to be relevant.
Okay, very
But
good
then also
question.
to-
Yeah.
But then also it seemed, so in your first example, it seemed very easy to break the symmetry with relevant operators.
Right.
Maybe not in the gauge theory, so they
Yep.
seem to be.
Well, it's also in the gauge theory, but let me answer that. So here the high energy physicist and the condensed matter physicist think about it differently. The high energy physicists don't care to impose any global symmetry you want. It'll be completely crazy. And then we just analyze the consequences. And if there are lots of relevant operators breaking the symmetry in the infrared, we couldn't care less. For example, we studied the discrete series, which was invented in this institution. We go very high up in the discrete series. There are lots of relevant operators at low energies, and it doesn't bother us a bit. We do want the model to be natural, namely to formulate at short distances a model that has some symmetries, and we don't care how complicated the symmetry is, and we can fine tune, etc. The condensed matter people have another notion of naturalness, which I think should better, they call it stability, I think it's better to call it robustness. Their view is that at short distances, we have some generic lattice model. It has no symmetries at all, or very little symmetries. And then at low energies, there might be emergent symmetries. So we'll be very happy if there is an emergent symmetry, but we should limit our understanding, or we should limit the discussion to those emergent symmetries that there is no relevant operator in the long distance theory that violates the global symmetry. If there is such a relevant operator, we'll disturb the microscopic Hamiltonian a little bit. This relevant operator will appear in the infrared. It will completely ruin our discussion. It's a totally different game. In one of them, you postulate whatever symmetry you want and you analyze the consequences. In the other, you postulate whatever symmetry you analyze the consequences, but then you also have to check for the robustness, namely what happens when you add a relevant operator. The examples, when I said that the high dimensional examples are more interesting than the examples I mentioned here, was precisely this point. The models I presented here are natural, but not robust. I postulated the symmetry and I analyzed the consequences. But if I try to break the symmetry, the whole structure disappears. The whole structure depends on the symmetry. So the symmetry was not an emergent symmetry. I postulated it on the lattice. In the higher dimensional case, and go to more interesting models in 3+1 dimensions, we postulate the symmetry on the lattice. We go to low distances, the symmetry is still there, we analyze the model. But then we realize that the low energy theory does not have any relevant operators violating the symmetry. In fact, in the more interesting models, the low energy theory is gapped, and there is no local operator acting in the space of ground state at all. Relevant, irrelevant is nothing. It's like in a TQFT in 2+1 dimensions. And therefore, the model is robust. So you found a point in the parameter space, you analyze it, you found this infrared theory. Now you deform the model in the UV a little bit, break the symmetries, so the model is no longer solvable. It's much more dirty and complicated. But when you try to map that to the infrared, there's nothing it could map to. So there's a neighborhood, there's a finite neighborhood in the space of coupling constants in the UV that's going to lead to the same answer. So this is a much more satisfactory situation. It does not happen in 1+1 dimension, but this is something that happens in the high dimensional examples. I hope I answered your question.
Maybe a final question.
So I understand you explained the right way of thinking about the system, but
Not the right, a better way.
but is there a path integral understanding of features such as this GCD that was appearing, for instance?
On the lattice is a path integral.
No, I mean, what? But
The
there's supposed
continuum of the lattice.
it's supposed to be a
No,
continuum.
so the continuum, I cannot get the GCD in the continuum because it's GCD with L. So I cannot do that. And in other cases, the formula is much more complicated.
Is there any reflection of that?
Okay, so what typically happens is that the continuum path integral, when you look at phi, you ask which phis contribute. There are field configurations which are discontinuous. And there it forces you to regularize it, even if you are in a continuum, to give meaning to the discontinuous field. So a lot of the stuff you can do in the continuum, but the discontinuities should be handled on the lattice. And when you do that on the lattice, depending on how you regularize, you get different answers. But this is only for this particular question. For the restricted mobility, you might not need to do that. Here.
Yeah. So your defects, they cannot move. They seem to form a representation of the gauge theory. Can you think of them as a one-dimensional lattice?
I could put,
And then,
so first of all, let me
the
correct.
operators that from that theory, not one you come to from the outside, but then the operators that get you from one defect to the other, you could think of them say as the nearest neighbor interaction or
So
et cetera,
there are no,
et cetera.
there is no, first of all, the defects are not transforming under the gauge symmetry. I was very careful to
No way.
formulate the whole thing in a gauge invariant way. So there's a global symmetry, not a gauge symmetry. The defects are charged under the global symmetry, not under the gauge symmetry. And when you discuss simple cases like Q1, you can be careless and you get away with it. When you get to these complicated things, it's not even the same group for the spatial pattern thing. As a group, they're not the same group. So that's the first thing. The second thing is that you cannot put, so normally you would say, okay, this is a defect, it's a Wilson line. It's a Wilson line in space, so the defect can bend. Here we don't have the Wilson line in space. What we have in space carries different charges. So the defect cannot move.
All right, let's thank Nati again.